Let us see the methods which comes under this digital data to analog signal conversion. And the first method is amplitude shift keying, where based on the digital data being transmitted, you can find the variation in the amplitude of the carrier wave. So here we are transmitting, or our input data contains both 0 and 1. So digital data is having 0 and 1. And assume that our input is 10101. So whenever the input value is 1, then you can find a carrier wave like this at fixed amplitude. Whereas when the input value is 0, then in that case, you don't find any amplitude or any carrier wave at all. Or you, even though if you find anything also, that will have lower amplitude than 1. So this is having some amplitude. So the amplitude which is less than this amplitude will be assigned to this binary value 0. Advantages of this method are it is simple to implement, whereas bandwidth efficient for low data rates. Whereas disadvantages, it is not suitable for very long distances without error correction. Second method is frequency shift keying, which is a modulation technique where based on the transmitted bit, like whether it is 0 or 1, there will be change in the frequency of the carrier signal. In the previous case, there will be change in the amplitude, whereas there will be change in the frequency. And in the diagram, you can see that. So let us take the same binary data 10101. So wherever we have 1, you can find more number of cycles with high frequency. So you can see the number of cycles. So more number of cycles, that too with high frequency, can be observed. Whereas if the binary state or binary value is 0, you'll just find fewer cycles. You can see the difference between these two. Compared to 0, in 1 we have more number of cycles. That too here it will be lower frequency. Similarly for 1, more number of cycles. For 0, less number, and so on. The advantage of this method is it is more resistant to amplitude noise than the previous method, amplitude shift keying, and it is easier to detect in noisy environments. Whereas disadvantages, it requires more bandwidth compared to amplitude shift keying. And usually this method is useful in radio communications, like radio teletype or caller ID signals, etc. And the third method is phase shift keying. So here, based on the digital data being transmitted, you can find out change in the phase of a carrier signal. And the frequency and amplitude, they remain constant in this. Only the phase of the wave changes to represent different bits. Here the process is, say if the input value is 1, then you will find a wave with the initial phase. So you will find some sine wave. And when the input value is 0, this wave phase will be flipped 180 degrees. So the same wave phase, you will see it. So there will be some kind of inversion or flipping. So this part, it will come to the bottom. And then the bottom one will move to the top. Again, this upper wave will move down and the lower wave will move up. So you'll find some kind of inversion or flipping in the wave. So again 1. So for 1, this is the original sine wave. Same wave will be represented. And when it comes to 1, again second value, the fourth bit also 1 only. So the same signal will be represented in the fourth case also. Whereas when we get 0, again inversion of the original sine wave will be represented. If it is 0, phase flips again. And advantages of this method are it is more noise resistant than amplitude shift keying and requires less bandwidth than frequency shift keying for the same data rate. And the second method is digital data to digital signal conversion. The method used here is line coding, which is a process of converting the digital data to digital signal. And these are some of the line coding schemes: unipolar, polar, polar, bipolar, multi-level, and then multi-line. First method is unipolar NRZ. Here unipolar means signal uses only one polarity and there won't be any negative voltage at all in this unipolar NRZ. So there will be only positive voltage. So if the binary value is 1, assign positive voltage. If the binary value is 0, voltage should be 0 only. Then non-return to 0, where the signal does not return to 0 at all in the middle of the bit period. So this is the bit period. Say if the signal is something like this, or if the signal stays constant for the entire bit time. So this is a complete bit time for this bit 1. If it remains the same, then we say that it is non-return to 0. Say for example, in the middle here, this is the middle part. So if you find a representation something like this from the middle, in the middle of the bit period, then this is nothing but, see here it is returning from positive to 0. So this is 0 level. So that we call it as return to 0. So if it remains constant for the entire bit frame, then that is non-return to 0. If you see a signal which is returning to the 0 at the middle of the bit period, then that is called as return to 0. Okay. So here what is the rule? If the binary value is 1, voltage should be positive. If it is 0, voltage should be 0 only. So you can see that. So first input value is 0. So it remains 0 only. Second value is 1. So remove this one. So it remains positive. And again for 0, it remains in 0. For second 0, again remains in 0. When we get 1, move to positive voltage. And when we get 0, again return to 0 and stay in 0. When we get 1 again, move to positive. Again we have second one. So it should be positive only. When we get 0, again go to 0 and it remains 0 only for the entire bit frame. For the entire bit time, it remains 0. And when we get 1, again move to positive. So again we have one more 1. Stay in the positive side only. When we get 0, move to 0. So this is how the signal will be represented. Second method is unipolar RZ, where there will be again same positive voltage for 1 and 0 for binary value 0. But here it is return to 0. So you will find return to 0 voltage in the middle of the bit period. So see this graph. So here when we get 0, then the value remains 0 only. Whereas for 1, you can find 2 halves. Okay, so as I said you before, this is a complete bit frame allocated for this value 1. So this is the first half and this is the second half. So if you see the first half, there is raise in the voltage. So it will be high for the first half or it stays in the positive. Whereas it will return to 0 in the middle. So let me show that to you clearly. So if you take the binary value 0, for 0, voltage is always 0. Whereas if it is 1, you need to consider two different partitions here because return to 0 in the middle of the bit period was there. So this is the complete bit frame allocated for this binary value 1. So this is the first part and this one is the second part. So for the first part, if the input value is 1, voltage will be positive. Whereas for the second part, voltage should be low. So high for the first half, whereas low for the second half, or always returns to 0 volts. And for the second 0 again, if it is 0 remains in the same state, second one again 0 remains in the same state. When we get 1, again you will find two different parts. One is for the first part, there will be raise in the voltage to positive, and in the middle of the bit period, you can find return to 0 from positive to 0. And after that, again we have 0. So 0 means remain in the same state. So voltage will be 0. Whereas for 1, again you will find positive, and at the middle of the bit period, you can find positive to 0 return. And after that, again we have 1. So again there will be change, or voltage will be positive for the first half, and at the middle of the bit period it returns to 0. For 0 again stay in the same state. Again for 1, first part should be positive, second part or in the middle of the bit period return to 0. Similarly with the second one also, and finally when we get 0 remain in the same voltage 0. Next method is polar NRZ level, which uses two voltage levels. So here we'll consider both the positive as well as negative voltages. And NRZ, as we saw, it represents non-return to 0. Here the signal stays constant for the entire bit time. And the level is, the binary value is determined directly by the level, which is nothing but sign of the voltage but not by the transitions. So this is the logic. Whenever the binary value is 1, voltage will be negative. When the binary value is 0, voltage will be positive. So here for 0, it should be positive voltage. When it is 1, you can see negative voltage. So this line is completely negative voltage. And again when we get 0, positive voltage, again 0, positive voltage. For 1, signal will be negative. For 0 again, positive voltage. For 1 again, negative voltage. Second one, negative voltage. From 0 again, positive voltage. For both the ones, negative. And finally, positive. Next one is polar NRZ invert. So here we basically invert or flip the signal voltage level when 1 occurs. So we'll see. So for the first bit, we are taking it as positive. So here we have first bit as 0. So when we get 0, it remains positive for the first one. And after that, when we get 1, whenever we get 1, there should be inversion or flipping in the signal. So 1 is represented in the positive voltage here. So there should be flip in the 1. It should move to negative, and 0 means it remains in the same voltage level until we get next one. So when we got this next one, again move to positive voltage, and when we get 0, remain in the same voltage until we get next one. So when we got this next one, you need to invert and move this one to, move the signal to negative. And after that, for the second one, it should be positive. You can just observe, for the first one, it is negative. For the second one, it is positive. For the third one, again it is negative. For the fourth one, positive. Okay, so there should be alternate negatives and positives for one value. And for 0, remain in the same voltage level. When we get 1, see the previous one is positive. So this one should be negative. Again, we have one more one. As this is negative, the second one should be positive, this one. And remain in the same voltage level for. Next one is polar RZ. So return to 0 means again you can find two halves. For the first half, voltage is either positive or negative. And for the second half, voltage always goes to 0. Say if the bit value is 1, first half will be positive and second half, as discussed in the previous step, it remains 0 for both 1 and 0. Whereas if the bit is 0 for the first half, value is or voltage is negative. See, first bit is 0. So 0 means first half is negative. So this is first half which is negative. So here if you see this, first bit is 0. So 0 means first half should be negative. So this is the first half which is negative. So this is a complete or the bit time allocated for this 0. Entire bit time allocated for 0. Out of that, first half should be negative, second half should remain 0. Then when we get this 1, first half should be positive, second half should be 0. So this first half is positive, second half should be 0. Next, when we get 0, again first half should be negative, second half should be 0. Again we have one more 0, so first half should be negative, second half should be 0. For 1, first half is positive, second half is 0. For 0, first half is negative, second half is 0. For 1 again, first half is positive, second half is 0. For one more one, first half is positive, second half is 0. Similarly for other binary values also. So you can even use this table for simplicity. Say this is the data given for us, like 0 1 0 0 1 0 1 1 0 1 1 0. So when we get 0 for the first half, voltage will be negative and second half voltage should be 0. If the binary value is 1, first half should be positive, second half should be 0. In that way, for all the values here, we already represented what should be the first half voltage and what should be the second half voltage. Next one is polar biphase Manchester encoding. So Manchester encoding is polar self-clocking line code where each bit is split into two equal halves. So here you can see how this bit 0, it is split, it is divided into two equal halves. And there is always transition in the middle of the bit. So in the middle of this bit, you can find transition. It can be either positive or negative. There will be some kind of transition. So if you take this bit 1, transition will be from high to low in the middle of the bit. Whereas if the binary value is 0, you can observe transition from low to high in the middle of the bit. So let us see this. So this is the binary value 0. So this is the first half. So for the first half, it remains negative. Whereas second half should be positive. So for 0, initially it is low. Low is nothing but this part. And after that, it should be high. So you will find low to high transition. And after that, when the value is 1, first you will find high transition. And after that, it will be high to low. For 0, low transition. And after that, you will find low to high transition. Then Again 0. So 0 means it should be low. So you will find low to high. And for 1 means high to low. If it is 0, low to high. Again 1 means again high to low. So for 1 again, high to low. For 0, low to high, and so on. So this is how the table will be represented. So if the binary value is 0, then first half should be low and transition should be from low to high. So obviously second half remains in high state. Whereas if the bit value is 1, first half will be high and transition will be from high to low, and second half will be low. Next one is bipolar AMI or bipolar NRZ, which is a line coding scheme. So here 0 is represented by 0 volts, whereas 1 it alternates between positive voltage and negative voltage whenever every time this 1 occurs. So we call it as alternate mark inversion. So you can see this here. So whenever the value is 0, voltage should be 0. So here value is 0. So voltage should be 0 only. And when we get 1, for the first one we are taking positive voltage. Again when we get 0, voltage should be 0. For the second 0 also, signal voltage should be 0. For 1 again, so earlier for this one we took positive. So you should observe alternates between positive and negative voltage. So for the second one it should be negative. Whereas for 0 again it remains 0. If it is 1, for the third one it should be positive because the previous one is negative. And again for second one, opposite of that is negative. For 0 it is 0, and so on. And the diagram looks like this. So when the binary bit is 0, voltage should be 0 only. If it is 1, for the first one positive, second one negative, third one again positive, and so on. Next method is bipolar pseudoternary, which is a line coding technique. This method is actually the reverse of the previous technique, that is bipolar AMI. So here the logical 1 is represented by altering positive and negative voltages, logical 0, whereas logical 1 is represented by 0 volts. In the previous case, 0 is represented by 0 volts, 1 is represented by positive and negative voltage. So this is completely reverse of the previous method. So if you take this, if you see the signal representation for 0, it should be positive, and when we get 1, it should be 0. Again, for the second 0, it should be negative. For 0 again, alternative 0. So previous one is negative. So this one should be positive. And when we get 1, it should be 0. When we get 0, again, it should be negative. For 1 again, remains in 0 only. Second one also remain in 0, and so on. So this is a table format. So when we get 0, it should be positive. When we get second 0, negative. Third 0, positive. Fourth 0, negative, and so on. For all ones, it should be 0 only.